Dear friends, I'm very honored to be invited to participate in Computer Graphics International Conference in 2022. I would like to thank to the chairs, online researchers, especially my tutors and partners. Thank you, everyone. Okay, the title of the paper is DDCNet, a lightweight network with variable receptive field for real-time portrait segmentation in complex environment. We propose a new model named DDCNet. It can segment portrait images in complex environments in real time while maintaining its low complexity and has excellent accuracy. Next, let me introduce the authors of this article. Our tutor, Professor Huang Dongjing, my partners Wu Di and Dr. Liu Jinhua. Thank them for their hard work in completing this paper. My name is Lu Yushan, and I am the presenter of this report. I will introduce our paper for 3 parts. Research background and current situation. Our methods, experimental results, and analysis. First of all, let me introduce the background of the research on portrait segmentation. Portrait segmentation is an important subset of semantic segmentation, which aims to divide images into portrait and background by classifying each pixel. Portrait segmentation is a pre-processing operation used to study and analyze human behavior, and it makes important contributions to subsequent studies such as 3D reconstruction and tracking recognition. In recent years, semantic segmentation network based on deep learning has developed rapidly. But it is still a huge challenge to create a network that balances real-time, lightweight, and accuracy. Because the segmentation task needs to solve 2 contradictory problems at the same time. That is, to save low-level features while acquiring high-level segmentic information. In order to ensure the effect of high accuracy, researchers try to place multiple receptive fields on layers of the network to enhance global and local information. But the parallel operation brings time consumption. Another common method uses a 2-branch network. The 2 branches are used to obtain low-level features and high-level semantics, but increase the model's complexity. To solve these problems, we propose a DDCNet module with deformable depth-wise separable convolution block and detail selection block. The DDC module proposed by us combines deformable convolution with depth-wise separable convolution, so that the module can automatically adjust the receptive field according to the characteristics of objects, so as to achieve the purpose of enhancing global and local information without time consumption. The parameters brought by deformable convolution and flops are offset by the feature of depth-wise convolution, thus reducing the complexity of the module. The DDC structure is shown in Fig 3. We first perform a pooling operation on the feature map to feature reduce the flops and memory consumption. Then use the depth-separable convolution to extract the offset. The resolution of the output feature map remains unchanged, and the depth becomes 2 times k². At this time, every 2 times k² pixel at the same position corresponds to the offset of the corresponding pixel in the calculation process. Substitute the offset into the depth-wise convolution to perform the operation, and then perform the point-wise convolution operation to change the number of channels. Finally, a linear interpolation operation is performed to restore the resolution of the resulting feature map to the input size. The DS module will propose sets two thresholds to remove the noise in the high-resolution feature map in the skip connection and retain the details that are discarded during the encoding process. So makes the supplementary detailed information effective and can bring better segmentation results to high-level semantics. Semantic segmentation modules mostly use an encoder-decoder structure. The encoder downsamples the input image to extract detailed information, reducing the resolution of the feature map. The decoder upsamples the small size resolution feature map to restore its detailed information and resolution. The detailed information lost during downsampling is difficult to recover perfectly during upsampling. The structure of our proposed DS module is shown in Fig 4. The DS block can calculate the confidence of the low-resolution feature map and propose two confidence thresholds to control the position of the pixel of the supplementary high-resolution feature map, so as to block noise from interfering with the segmentation result. Specifically, the DS block uses the softmax function to calculate the probability value of each pixel for the two categories of the feature map with the number of input channels of 2, and store the position of the pixel with the maximum probability value less than P1 as the information set A, and store the position of the pixel with the difference between the two probability values less than P2 as the information set B. Perform a union operation on A and B to get the detailed information to select the set C. Multiplying C with the high-resolution feature map for pixel correspondence, and the result is spliced with the low-resolution feature map, which introduces the details of low-level features to the high-level semantics, while avoiding the inflow of the information of the pixel where the noise is located. We set P1 to 0.9 and P2 to 0.3. At this time, the network can obtain the best segmentation results. We evaluated our network on the public portrait dataset EG1800. Fig 5 shows the visual segmentation results of DDCNet and other lightweight models. When the person in the image is occluded by the object, the segmentation accuracy of the ESPNet, FAST, SCNN, and SINet model near the occluder is affected. MobileNet v3, Rethink BISENet, and PortraitNet have obvious phenomena of incorrect classification of pixels in the foreground or background. DDCNet can better identify people and occlusions and perform segmentation without generating classification errors. BISENet v2 and ENet are inaccurate in the segmentation of character boundaries, and DDCNet classification is more detailed and correct. Experiments show that the segmentation quality of DDCNet is better than other models, and it has the best and stable overall performance. Figure 6 shows the ROC curve and PR curve of DDCNet on the EG1800 dataset and the video conference segmentation dataset. The AUC value on the EG1800 dataset is 0.9873. The average accuracy is 0.9904, and the AUC value on the video conference segmentation dataset is 0.9985, and the AP is 0.9956. In order to qualitatively evaluate the experiment, we use the parameters, flops, FE score, accuracy, Recall MIOU, AUC, and FPS as performance evaluation indicators. Table 1 shows the comparison results of our model with other models on the EG1000 and 800. Our model effectively controls the parameters and flops while achieving superior results in real time. In all comparative experiments done the EG1000 and 800, our model achieves the best F1 accuracy and AUC values. We applied our model to the conference video segmentation dataset and achieved excellent results. The results are shown in Table 2. Experiments prove that our model has good generalization ability for portrait datasets in different complex environments. We have also done some ablation experiments to find the optimal parameters in the model. Please read our paper for details. In the next step, we will continue to expand our work. We will pay more attention to the complex and diverse structure of the portrait boundary and the occluded objects in front of the portrait, and integrate the method into the reconstruction workflow. Thank these researchers for their work. This is all our work. Thank you for attention. It would be a great honor if we could help you in your work.